I don't assume you are going to be able to understand absolutely everything. I just like you to try to follow along whatever happens, and in a kind of high-level way. Then you're going to be you actually need to spend some extra time by your own and try to understand what's going on. Okay? All right, so let's go to the second part of our talk, which is going to be artificial neural nets, and we start with the supervised learning classification in this case. So we're gonna try to do some fun stuff, okay, and see how neural network try to solve this kind of problem. So our initial point is gonna be trying to generate nice colored spirals, right? Because everyone likes nice colored spirals. So if you just draw this guy, the equation of this guy is simply a parametric formula of this form, right? So it's nothing fancy. You just have like a sine cosine term, which is starting from, goes up to 2t, where t goes from 0 to 1. And then you have that, it goes from actually 2t divided by c, where c is the number of categories. So in this case, capital C is 3. So we have 3 different categories. We have 3 different branches of that spiral. And they go up to basically 2 divided by c, which is 2/3. So this first guy, it starts in this direction here, and it goes like 1/3, 2/3. See? So it ends up here. This guy, second one, it starts this direction. This is first third, and this is second third, so it ends up there. And the last guy here, it starts with this direction here. This is going to be my first third, and then this is second third. So as you can see, with this parametric formula, we can express that pretty drawing there. All right. So now we know how to draw some lines. But we need to get some data, right? Because anytime we'd like to perform supervised learning, what did I say before? What is supervised learning? We have a sample
with labels,
and we have a label, right? So what are my samples here? So I'm going to start now generating these samples. So I get the same thing here. It's the same formula, I think. Yeah. I add some disturbance here, some noise. And so this is whatever ends up looking like. So these are going to be my data points. So one data point here is going to be a point in a plane, right? So each of these points here is represented by a x and y coordinate on this space. And the label is going to be basically specifying whether this point is purple or it's red or it's yellow, right? And what we'd like to do is basically train our algorithm in order to assign the correct color given that I provide a position on the screen. Okay? So all this collection of points are going to be my training points, my samples. And the samples are expressed by 2D coordinates. There is the x coordinate and the y coordinate. The point at the end is going to be having a machine learning algorithm, in this case a neural network, which given a two coordinates, like an x and y coordinate, is going to give me a categorical value, which is going to tell me, oh, this point here, I think it should belong to the purple spiral, it should belong to the red one, it should belong to the yellow one. Okay? So we are just trying to categorize these points as belonging to a specific spiral. You can play with the code later on and add more spirals, add more points, less points. You can play a lot and understand better the difficulties of this problem. But so far, it should be clear, right? So given a point in the plane, we'd like to learn the color of the point, right? And the colors we learn by using the C. So the C is the class, the specific class, and the capital C is the number of total classes we have. All right. So what we are going to be trying to do, so what we hope the network is going to be performing is some sort of division of the class, of the space. So in this case, I'd like to say, oh, everything that is here belongs to, let's say, if I just look to this small region, everything that belongs here is red, everything that is here is yellow, everything that is here is purple. The issue is that those spirals are not linearly separable. So if I just draw some lines and I say everything here is red, well, not really. stuff red is happening here. Here we have some purple. We also have some yellow. So whenever you use let's say a linear classifier, so it would be basically just drawing some lines like this. And we're going to be soon seeing that neural networks are simply somehow stacking multiple linear classifiers together with some non-linearities in between. But basically, what we are trying to do is draw some lines and getting data to stay within some specific region. So how does a neural network perform this stuff? A neural network will do this, basically. It gets the space, and it starts rotating the space in order to disentangle those representations. So anytime we use a neural net, we have some kind of disentangling operation. And at the end, I can simply use a linear classifier as the one that is shown in the last animation. Over here, I can say everything that is yellow here, everything that was here, it was purple, and everything that is above here is red. Okay? So my last layer in a neural net is a linear classifier, again, which is drawing those three lines. And the other layers in between are just performing this kind of dewarping. So someone can say, ha. Someone say, ha. Okay, never mind. I know how to rotate things, right? How do you rotate things? You're a physicist. You know how to rotate stuff. With matrices, right? Okay, very well, right? So if you come here and you rotate this spiral, what's happened? It's like you have those kind of wind things.
Same thing.
So they still rotate, but they don't disentangle. Is a question there?
Yeah.
You can ask the question.
That last slide, was that a real deconstruction of a network that solved this problem, or was that just your animation?
It is actually going between the first layer to the last layer and back to the first one.
So the answer that you found, the program that you found to solve this, literally does exactly that transformation?
Absolutely, yeah.
Okay, cool.
So, and that's what I was going to say. But how I drew that is not that way. I mean, you can do...
That's an interesting question too, yeah.
To make things look pretty, I draw them my way, but that's how the network is going to be.
I see, so it is a cartoon.
It's a cartoon, but I'm showing you not cartoons in 1 minute. Okay. So, yeah. So, yes and no.
It was advertisement and the real cartoon will come later.
That's correct. And they look exactly the same. So, but this is like what we hope it does, right? So the problem here is that if you use a matrix, you can rotate this guy here, but it's going to be like those little colored things with the air, right? They still rotate, but the things are still intertwined, right? And the thing that we are actually aiming here is to rotate the space and warp the space with different kind of rotation given the different position from the center of the space, right? So we have a non-rotation here and a stronger rotation as we move away from the center, okay? So basically, the neural network is going to perform some kind of space warping through the layers. This is basically seeing things from the input space. As you move across to the output, this is the output space view. Back to the input, back to the output space. If usually, this is not the way you see those things. The way you usually see those things are from the output of these networks, which are these kind of graphs. So this is my network training. At the beginning, it doesn't know anything, and as it trains, it tries to shape its own understanding by following this drawing. And this is not a cartoon, this is actually the training part. So the point is that this shape that it has learned, basically, this is like looking at the output from the input. That one basically is just looking through the network. But they are basically the same operation. So we are trying to basically have a network which is going to be learning that this region here belongs to the yellow, this region belongs to the purple, this region belongs to the red class. And is it clear so far? Are you excited? Shall we move on? Very well. And then, training data. No, let's make a demo. So I'm going to show you something cool here. Possibly. Yes. So I'm going to go back to my notebooks, and I'm going to be just running quickly the space stretching. So here, I really don't want you to read anything. I'm just showing you very pretty pictures. Okay, so this is my initial distribution. Here I had just some Gaussian points. Okay, so you had just a spread of points in the two direction with diagonal matrix with unitary variance. Okay, just points in the center. Just forget whatever I said before. If you multiply those guys by a matrix, what does it happen? So someone said, oh, use a matrix, right, for rotating. Well, that's yes. So here I multiply this stuff by a matrix. This is my input. Here is by this guy. This guy has this eigenvalue here, right? 2.6 and 0.3. So you get the 6 and the reduction in the other direction, right? So this is whatever happens with that. Whenever you multiply by matrix, you get some squash in one direction, you get some stretch in the other direction, you get also some rotation, right? But everything is rotated the same way in the space because it's a linear transformation, right? Here you have a different matrix, so you have a very, very, very tiny eigenvalue in this direction, a very large eigenvalue the other one. So this is nothing new, right? This is simply matrix multiplication with very pretty colors, right? You like the colors, right? Good. All right, so more matrices, more matrices. So here, both of those eigenvalues are very large, so everything gets expanded. So you understand, right? Small eigenvalues, things get collapsed. Larger eigenvalues, things get expanded. And so on, blah, blah, blah. Very nice drawings. All right, so how can we do that in PyTorch? So in PyTorch, we do exactly the same, but we use something that is called nn.linear. Can you see here? So nn.linear is just using a matrix and multiply by your input. Exactly the same. So although it's called nn, just forget. It's just a linear transformation. And here, exactly the same. This is one of the basically examples we have seen before. All right, so let's do something more fun. Let's introduce a non-linearity. So in here, I just multiply my x with identity times s to scale. So this is my scaling matrix, which is just scaling. It doesn't rotate anymore because it has the same guy in both directions here. And we have a tan h. Do you know hyperbolic tangent? Right? Okay, good. All right, so let's try to run some stuff. Okay, so this is my hyperbolic tangent first. Everything that is below -5 is basically set down to -1. Everything that is above +5 is basically 1. As you approach the 0, you get basically a linear part in the center, and you get this kind of S shape. So this is also called a sigmoid function, sort of. All right. So, and let's put here a sequence of a linear transformation. Can you see here? And a tan h. Okay. So let's see what happens here. So here I have my input, which is my scatter in the two direction. And here I have my scaling factor equal 1. So I scale things a little bit. Actually, I don't scale. I have the same scaling, but then I use this tan h. So things that are above here get pushed to 1. So everything that is outside the +5, we have said, it goes to 1. So everything here goes up to 1. And things that were below... okay, let me show you the other graph here. So everything that is outside this region, it gets pushed towards 1. Everything that is in this region gets pushed to -1. The same for up and below, right? So we get this kind of nice cloud shaped as a square here. Does it make sense so far? We are applying a nonlinearity to some kind of zooming factor, right? So what does it happen now if we increase the zooming factor?
It will go more.
There you go, correct. So everything goes more. And if I push more, everything goes even more. And even more, right? And even more. And again, you understand, right? So the whole point here is that we have converted that initial cloud, which was very dense of many, many things. We pushed everything on the side. And we have a few samples here that are very, very disentangled. So here you can already see how things get pushed away, and we have different stretching in different regions, right? So here these guys are very stretched, and here things are very collapsed. Remember before what we were trying to do? We were trying to warp with different regions. The same thing we see here. Here things are very expanded, and things here are very collapsed, right? So if I go up above the other one, here you can see a more smooth transition, right? Here, things are very, very, very pressed together, and here are much less pressed together. You can also apply some rotation if you don't have just the identity matrix there. Okay, so this is just showing you how I map a cloud of points into a square. And the nice part is now that if I'm just running a neural net, basically a sequence of a linear mapping, a non-linearity, and a linear mapping just with random weights, without training anything, and I apply this stuff to my little cloud here, you're gonna see some very pretty pictures. So this is simply a random neural net applied to that initial cloud, right? So these are my initial points, and here I apply these 2D coordinates into my network, and this is the output of my network. And you can see here just uninitialized neural nets can perform some very nice squashing and pushing data around. Okay, so we are going to be using this stuff in order to push space around and dewarp that spiral in a bit. Questions so far? No? Are you with me? Are you sleeping? Are you okay? Are you interested?
Yes.
Okay, good. All right, so
Is there an intuitive explanation of why there seem to be different numbers of lines in these? So that seems to have like very clearly two edges, maybe.
Yes,
to a point.
yes. So if you check here, there is a number which is called number of hidden layers. So in here we go from dimension of 2, which is the space, input space, the coordinates on the plane. We go up to 5 dimensions, which is a 5-dimensional space, and then from 5-dimensional space you go down to 2. So when you have this kind of expansion, you can start pushing and moving things around, and you get a lot of degrees of freedom there.
So was each of these images the output of one of the layers?
Those images that you just see there, they are simply random initialized matrices with a non-linearity in between, and I feed them inside, and I just show you what a neural network can perform on those points on a plane. Okay.
And the color text stays with the point. Right?
The color stays with the x direction of the initial position here. So the color here express
of the initial.
The initial
so it
x.
stays even
Yes,
after.
yes. All right. So all we have to do now is basically get some kind of control over how these networks perform this kind of funky shapes, right? So if only we would know how to change those parameters in order to enforce some specific dewarping, right? So all we have to do now is get in those spiral things and start performing some dewarping, which allows me to dewarp that kind of intricate spiral. And that can be done very easily with Torch, just with a few lines of code. All right, so how much time do we have left?
Half hour.
Half an hour. Oh, okay, it's a lot. All right. So we have understood that these neural networks, even if they are not trained, they can perform some space.
Okay. It was completely empty. I was
Yes,
surprised.
I'm aware. I can see. Thank you. All right. So we have seen now that these neural networks can perform some kind of space warping. No, they get some points I showed you before, and they map them in different regions. And we have now to control them. We have to enforce some way in order to move those points in specific ways, right? Those warp things, we won't like to move them around. And so let's just do that. How? The few next slides. So,
just one question.
Yes.
So when you're making this movement, if it's not, should it be always area? Should it be connected or not? You understand what I'm saying? So when you have a movement, if you have 2 points which are connected, they always will stay the same. But if you have, for example, with this dot, one area which is red and around is blue, and again around is red, then you don't have movement which will put all red together. So.
Okay, very well.
You
Yes.
understood?
Yes, I understood. So I'm trying to repeat the questions. So here, the guy in the first row, he asked, so if we have some points in the center, let's say red points here, then we have like a crown, like a ring of green points, and then we have external other points in red. How would we manage to move these guys? So can we put together things that are not on the same plane?
Not connected.
Not connected. So can we do something like that? Yes, that we can by adding additional dimensions. So we were on a 2D plane, but if you switch to a 3D plane, you can get the red stuff, which was the ring. You pull it this direction, and the other guy, you put them here. And this way, then you can just cut this way. Okay. All right. So training data, we need to now put the data in a way that we can use it for training. So first of all, we are going to be defining a matrix, X, which is it's called design matrix. In my rows, I have those kind of X with a bar, which simply represent vectors. And here I have my first vector, which is like the coordinate of my first point in my spiral plot, okay? So I get the first point there, and I put here, one number, two number, second number. Then I get the second point, number 2, I get the first coordinate, second coordinate. And I go down until the last point I have in my spiral, first coordinate X and second coordinate, okay? Are you sure you understand? Okay, very well. All right, so this one is simply the collection of all my X points. How many points do I have? M. So M is going to be representing the number of training samples I'm using for training my system. What is N? N, instead, is the size of my features. In this case, since we are having points in a space, in a plane, the N is going to be just 2. We have 2 coordinates, right? So in this case, given 2 coordinates, X and Y, and given M examples, I'm going to try to learn those 3 different labels. Okay? Right, good. Second point, we have to see which are the labels of the classes. So for every example here, we had the 1, 2, up to the M example in my dataset. I have my C1, so it's the class of the first example. Then I have C2, second class, CM, last class. So sorry, the last example. So this one could be red, this can be purple, this could be yellow. Okay. So these are categorical, like bit of information which are connected directly to my design matrix. So therefore, this is a matrix of size m times n. Whereas this guy is simply a vector of dimension m. Good? Yes? All right. One more. So what is this? All right. So these are actually my real labels, because this guy here represents whether it is red, it is yellow, it is whatever. But I have to represent this kind of information in a more computer-like way. I cannot say, oh, this is red, this is yellow. So we are going to use these kind of Y vectors. So there is a line underneath. If I just draw them with a computer, I just make them bold. This is just to show you they should be bold if they would be drawn by computer. So this is my label, which is somehow built with this guy, associated to the first example. This is the computer label for the second example, and so on. So we have M labels, and in this case we have capital C classes, items. So can you guess what is going to be the representation of the label for the machine? Does anyone can have an idea? Could be RGB, but let's say it could be 1 to 3. But again, 1 to 3 it infers some order. So 1 comes before 2, right? And here I already show you that the size of these guys is capital C.
One hot.
It's going to be a 1 hot encoding. What is this stuff? So this stuff means if you belong to the first class, you're going to be a vector 1, 0, 0. If you belong to the second class, you're going to be 0, 1, 0, and so on, right? So I just draw a 1 when you belong to a specific class. And in this way, I don't enforce any kind of categorical sorting order, okay? And this is called...
Sorry.
Yes?
Are we doing this like to give probabilities at the end?
You don't have to, but this is in order to be defining later on a cost function, which we are going to be using to train the system. But yeah, it can be used for a probability later on, but okay, you can see this one about as like what is the probability of this point to belong to the first class? Is 1, so 100% first class, 0%, 0%, okay? So it can be also expressed and thought about in that way. Okay, so far, good? Yes, no? Yes? People are not moving their head. Okay, someone is moving their head. So someone is still alive. All right, so here, xi, which is my ith sample, it's simply a point in Rn. And in our case, it's just n is 2 because it's a point in the space. M instead is the number of the samples in the data set. In this case here, my y instead is like belonging to Rc, where capital C is the number of classes, and C is, well, it actually is not Rc, it's going to be like a set 0, 1, right, times C, power to the C. And C in this case is 3 because we have 3 spirals. And the last one are going to be my classes Ci, which is like basically a number from 1 to capital C. All right, so let's move on. So in here, I would show you how to draw the spirals with torch. I think we can move on because it's simply just drawing those spirals things. I think it's more cool if we are going to be actually getting some results. So I would recommend you to just go through the data generation by your own later on after we are done. So let's see now, finally, how and what are these neural networks, right? So we have spoken about those cute and fancy things, but let's see how they work. So in here, I show you a 3-layer neural network. This guy here is my input X, which is fed inside this second guy here. So we have 1, 2, and 3 layers. There is one guy in the center, which is called H, because it's hidden in the center of the network. And then I have here my output over on the top. Networks go from the bottom to the top. If you see them drawn from top to bottom, you're wrong. Just stick with this notation, please. All right. So what is the equation that is basically governing this neural net? So my hidden representation H is simply a nonlinear function f, which is pointwise applied to this guy here. So this guy here simply is an affine transformation on this vector x, right? Do you understand this nomenclature? I mean, you're all physicists and you already seen matrices.
We know what is affine transformation.
So you know, right? I mean,
Others also know, not only me.
Who doesn't know what an affine transformation is? Just to see, you know, right? You're not undergraduates. I mean,
we somehow little bit graduate, yes.
All right. So I just keep going, right? Just stop me if.
Okay.
All right, thank you. Because I'm not sure. So here we have an affine transformation of my input x, right? I have a bias term, which is just shifting, and I have a linear transformation here. I call WH, which is mapping my input to the hidden space. And here is a nonlinear function applied pointwise to every element of this vector here. The same way, I just keep doing the same operation, and I have my y hat, which is my predicted output, which is again a nonlinear function applied to this affine transformation. And this affine transformation is applied on the hidden space, hidden layer. Okay? So you have an input, affine transformation, nonlinear function, affine transformation, nonlinear function, output. Good? All right. Yes, question?
So why the hidden layer? Why not just have a nonlinear function from input to output?
Say again?
Why do we need a hidden layer? Why can't we just have...
Because you would have shallow networks and they don't... so if you have one layer only, you only can do the squaring thing. And you can only do... So if you have a affine transformation, you have seen before, you can stretch things, you can push them, you can rotate, but you cannot do warping, you cannot do those fancy diagrams we have seen. So as soon as you stack two guys of this guy, those two guys here, you start seeing all those fancy behavior that those neural networks that I just generated before without any kind of meaningful weight were showing. Okay, so that's basically it. So this is a neural network. Oh, there's no much more than this. We're gonna see some more stuff tomorrow, which we are gonna be introducing other cool stuff, but that's pretty much it. Everyone is okay with this thing? No issues, right? We are not afraid of this guy. Right, good. All right, so what are these guys? Simply, I guess you know. So this guy here maps from the input space, the n, to this d space, which is our internal dimensionality. And therefore, my bias is going to be also on size d, right? Because we are going to be summing like this linear transformation going from n to d, and then you want to sum also d. And the same guy here, right? This is going to be outputting C classes because we are going to be expecting that kind of one-hot sort of representation. So C classes going from D. And then the other guy here is going to be also capital C because it has to be in the same size given that we are summing. All right, so what are these f and g's? These f and g's are, again, nonlinear function applied point-wise, so for element-wise. They can be simply the positive part of a function. They can be a logistic sigmoid. They can be tanh, the one I showed you before. They can be some Boltzmann like distribution thing. You can just put there any kind of nonlinearity. So some are more used than others. I won't go into much details. This one is very nice. You know, so you're physicists, right? All of you?
No.
Not all. Who is not a physicist? But you know Boltzmann, right? Okay, so
Personally, yes.
all right, so you know this guy. So this is simply a Boltzmann distribution. All right, and so the overall, the summary of this slide is that basically my y hat, which is my prediction here, is basically a function of my input, which is fed down there, and then y hat goes from the input space to this kind of categorical space where we are representing different classes. And here we go again, mapping the input to its own class. Okay. All right. But this one can also be seen as mapping n space to a d space, which is potentially larger, and then we go out to the final capital C class, where the dimension of the internal space is larger than these guys here. So we go from 2 dimensions to a larger space, maybe 5 dimensions, and then we go down to, actually, we go to 3 because it's our 3 classes, right? Questions so far?
Is that necessary for the intermediate layer to have higher dimension than the...
So yes, for the reason he asked before. So how would you separate things that are not connected? So you need to push things in a higher dimension. This is very true also when you deal with like even larger inputs like images or audio and all those things. You really need to go in larger dimension in order to move things. So if things are in small dimensions, you cannot push things around because everything is like just packed. So first, push everything away, like larger space, and then you can just get things and move them around much easily. So it's not, as soon as you increase the number of dimensions, you have much more freedom of pushing things in different directions without being constrained of moving other stuff. Okay. Other questions? Yeah.
How many dimensions should you pick? Like, how do you know? 5.
You cross-validate. So you're gonna be trying empirically and see what it works better. Other things, other questions? Yes?
So how do you determine the bias term?
I didn't tell you anything, right, so far. These guys are coming from the sky, no? Someone gave you. So no one told you anything. I haven't said that. Other questions? Are you ready to see how we train this stuff?
Yes.
Are you excited?
It depends what we'll see.
Okay. He's not hired. I don't know this guy. We didn't prepare this before. All right. So again, then you're gonna be bored, right? So this guy is 2-dimensional because it's a point in the space. This guy is 100-dimensional. Means we have so much freedom. And the last one there, it's a 3-dimensional because there are 3 classes. All right. What's next? I guess it was the tutorial. Let's skip that.
So you are putting 2-dimensional space in 3-dimensional space.
Yes, but going through the 100, right?
I
go from 2 to 100 to 3.
Okay.
Are you okay so far? All right.
But you're going from 2 to 3, so I mean 2 is just 2, oh I see, 2 to the power of, okay. So you're just going from a 2-dimensional space to a 3-dimensional space.
So I go from my point in a plane to a probability defined over the number of classes.
I see.
This is what I do. So I start from 2 dimension and I end up with capital C classes dimension. Okay? So n dimension to start, capital C to end up. Other questions before I go on? There you go. All right, so I'm skipping all the demos. And so this is the Boltzmann equation I showed you before. So what is the softmax? Softmax over a vector, it's simply the exponential of that specific element divided by the summation of the all other exponentials. So this one basically, given a vector of whatever energies, you get the distribution of probability on which on those energies. Okay.
Should there be minus?
So actually, yes, there's gonna be a minus. We don't care because we just learned the negative energy. So yes, absolutely, there should be a minus if you're a physicist. I'm not, but yes, yes, you can put a minus. Nothing changes. Those are called, just for convention, logits. So that's the definition of logit, is the input of the softmax.
I'm confused because you say that it's either 0 or 1.
No, I see this is an open,
Oh, the
open
interval
interval.
0 to 1. I'm sorry.
Yeah, 0 to 1 excluded the...
Right.
All right, so what is this stuff? I define now, finally, something. So we are going to be defining a cost, a loss function, so that I can run a optimization something, an optimization program, which is going to be trying to minimize a specific cost. By performing this optimization, we are going to be basically straighten up that final warp space, the kind of spiral, right? So the whole point of defining this loss here is going to be basically telling the network how we'd like the final result to look like finally, right? So we have to define, we have to ask the network, okay, network, please perform a specific task. The task is going to be try to lower as much as it can this kind of cost. By lowering this cost, it's going to be translated as in warping that space accordingly to different strengths. Okay, so this is like the without mathematics. Now let's try to see what is this. So I have here my loss function, capital L, defined on the whole capital Y, which is the whole set of labels. It's just the average of those per sample losses. Okay, so this is an average of those per sample losses. And my per sample loss, it's simply the minus log of the correct class on my prediction. What does it mean? Let's see an example. So this is also called cross entropy or negative log likelihood. So let's see by example. We have my input here, an x, and the correct class is 1. And so my the correct label should be 1, 0, 0. Okay? All right, so let's say my y hat produces something that is very, very similar to 1, 0, 0. Okay? Very similar. So how is this loss performing? So we are going to get the minus log of the correct class. The correct class is 1, right? So if I do minus log of this guy, so log of something slightly below 1, how much is it? Log of 1, 0. Log of almost 1, a little bit below, minus 0, right? And given that we have minus here, we have 0 plus. Okay? So given that our network produces an output like this one, with this kind of function at the end, then the loss is basically 0. A little bit more on the 0, but yeah, just 0. So if we predict the correct label, then the loss associated to predicting the correct label is 0. Right? Good so far? Yes? No?
Yep.
Yeah, okay. What does it happen if we predict a wrong label? We are going to have the loss on something that is almost 0. Almost 0. What is the log of almost 0? A bit negative infinity. Then we have minus here. So we're going to be having this guy tending to plus infinity. Okay. So predicting the wrong label basically gives us a very, very, very high loss. Predicting a correct label gives us a 0 loss. Okay. So now we have this guy here, this average loss, which is the average of all these per example losses. And these per example losses are going to be the lowest whenever we have correct predictions. And they are very, very large whenever we have wrong predictions. Okay? Good? All right. I know, stay with me one more slide. And just, I still, just borrow me your few neurons that are still working on your brain, and let me finish up. All right, the last slide, seriously. So here I define my set of parameters as the collection of all these guys here that I showed you before, which are just initialized with random values. They don't have specific values. It's like my neural network you have seen before. So the networks I showed you before, they were just randomly initialized neural nets with random values. And you were seeing those very fancy kind of diagrams, right? What we are going to try to do now, we are going to be defining a kind of different loss function here, similar to the one we have seen before, in order is parameterized by this guy here. And then we're going to be changing this guy here in order to minimize this loss. Okay? I'm going to be a bit more specific here. So here I'm defining this loss here, J of theta, as the previous L as on the y function of theta, right? So these are my predictions, which are a function of my parameters, right? And that's basically saying, okay, this is my loss expressed as in labels, true labels, and my predictions, and this is my loss defined in the parameters I'm using. So it's simply just, bless you, it's just simply changing the variables, right? Here the loss is defined as predictions and targets. Here the loss is defined as function of my parameters. Okay? Yes? No? All right. Are you sure? Okay. All right. So more drawings. We can think about this loss. For example, if we have one direction only, I have my lowercase theta, perhaps like a quadratic function. So if I'm here, how do I reach the minimum? How do I get here? I look where is the slope going, right? So I just go down the hill, right? How do you look for the slope? You check, what is it? What is this point here? What is the slope here? The slope here is going to be the derivative of my loss with respect to this guy right here, computed in theta 0, right? So this guy here expresses me the slope here. And if I'm here, I'd like to go that direction, right? So here the slope is positive, and I'd like to go to that direction. So if I have positive numbers, I'd like a minus here. So I go there. If I'm here, my slope is negative. So I put also a minus here, so I know that I had to go to positive numbers, right? So here we observe that in order to find the 0, we'd like to step towards the direction of negative gradient, whereas of the loss function with respect to the parameter. I know, it's a mouthful. I hope you understand. Shall I repeat? No? Is it good? So it's just an optimization problem, right? All right. Finally, this is called gradient descent. You step towards the direction where the gradient is pointed against to. All right. So what are these guys here? So this guy is partial derivative of my loss function with respect to this first parameter here, which is basically, chain rule. And so it's just the loss by the y and then dy in the w. And this guy, given that is the previous h, is going to be still the chain rule, no? And that's why we use PyTorch, because this guy here, this is called backpropagation, which is just the chain rule, and which is performed automatically by PyTorch. So PyTorch, whenever you perform operation with those tensors, remembers what operation you have performed. And therefore, if you have a sequence of operation, it's just basically as having a computational graph. Whenever you have the last guy, you can go back, and you get basically this expression here, automatically computed for you. So We use PyTorch because there is a automatic differentiation engine behind those tensors, and it can memorize all the operations you have performed on those vectors, so that we can perform backpropagation with simply one line of code. And that was my last slide of theory. I'm gonna be just showing you that this stuff actually works, if you would like. So shall we go on and I'll show you? Okay. I don't care if you have questions, you're gonna see me later, because otherwise I won't show you anything anymore. All right, so back to the notebook here. I'm just gonna be running the spiral classification. Is the fourth actually. I skipped the automatic tutorial, automatic differentiation. So this one I was going to show you how those computational graphs are generated and how the chain rule is computed. But I guess you can go through that by your own. So here I'm just executing every line of this code like that. And there we go. So first part, which we skipped, was the generation of this data here, which is defined in a previous cell. And I just draw exactly the thing I showed you before in the presentation. Here we are training our network in order to minimize that J function, J of theta, with respect to those. So we are basically updating those parameters in order to step towards the direction that is not pointed of the gradient, right? In the direction opposite of where the gradient is pointing. And so we are going to be, I show you here that this network is simply a it has two different linear layers with a nonlinearities in between. And then here, if I show you how it worked, well, sort of, not really, right? So it tried to, but it's still linear, right? What's wrong here? So if we check the model, here. So if you see this guy, my input x goes through this guy here, a linear, and then goes through another linear, and then the output. So I have two linear transformations. Well, nothing works, right? Because it's just linear. I want to warp things. So what do I have to add? A nonlinearity, right? So I put here a nonlinearity in between, and that's it. So we go down, same two layers network, right? I go down here. Here you can see my output. My output here of this first affine transformation, it goes through a positive part function, and then the output of this positive part, it goes inside the other linear layer. So we have an affine transformation, a positive part, an affine transformation, and then output. Okay? So we just put a positive part between those two linear layers. That's all I've done. We are doing exactly the same thing, but can you see here?
Accuracy is wrong.
Huh?
Accuracy, it should be bigger or lower? Which one is better?
Accuracy.
I feel better, okay.
And you should. Right. So this is exactly the thing we have seen a few pages above with the three lines where there was no nonlinearity. Here I just added a positive part nonlinearity, and you have automatically that the network learns how to curve its own decision boundary in order to achieve the highest, well, actually to achieve the lowest loss possible on the training set. Is it clear? So the only difference between this guy here, which couldn't basically classify, we got like a accuracy of 50%, which is not that bad because we have three classes. 0.3 would be the random guess. And so this one is the best performance you can get with linear models or shallow networks. And just using two layers, the same two layers we have used before, by adding the positive part nonlinear pointwise function, we are managing to curve the space and perform this very nice separation. Questions? Yes?
It looks like the model is slightly overfitted if you extend past the point in which the data was generated from. Do you have any idea why that would be?
You mean this one, right?
Yeah, so like it goes right where the data ended.
Right. Because that's a very good point. So the model capacity the model we are using is actually a very, very tiny model. There are just 2 layers, and actually the dimensionality, 100 dimensions, maybe it's fine. So the 100 dimensions shows you this kind of curving here. But then all the power, the modeling power, has gone into shaping this curve here in order to maximize this separation of those points in these classes here. And you're saying, why didn't this guy perform anything? Because here, anything it does, this little curvature, it doesn't improve the training loss, right? So if this guy goes this direction, or this direction, they don't change the training loss too much, but they are actually changing a lot how well you manage here to shape this curve. So the more you curve here, the more you curve here, and the less you can curve here. So you have always kind of a trade-off between how well you can characterize parts here, whether you can characterize in other places. Then it's correct. This is just my training set. I didn't show you like where are the actual points belonging to a validation set. They may be here, and we have like perfect generalization, or they may actually happen to be here, and then we are going to have a very poor generalization.
Can we decrease 100 up to 50 and repeat the same?
The dimensionality, right? You said the hidden dimensions.
Hidden dimensions. So first I want to decrease to 50, and second increase to 150. But I don't know how much time it will take, but for 50 it's possible to decrease, right?
So that's why you have the notebook, right? So you have the notebook on your computer.
Yeah, but first I need to manage to run this. So if it's easy, let's try here. And then others also will see.
Of course. Here. So here we have defined dimensions 2. No. Hold on.
It's not it's a dimension of the plane.
Hidden units.
Yeah, I don't know where it's defined. Hold on.
It was H. It was H.
Oh, capital H. Okay, I see. All right. Capital H. Here, number of hidden units. Yes. So you wanted 50.
For example.
So I go here. I generate this guy with 50. There you go. 50, same, almost.
No, it's lower, but
Oh, okay, you can see here there is much less of a turning, right? So also here there is much larger region where the space is not bent here and here, and the same here. And then if you actually enlarge this view, you're gonna see that this stuff is gonna be linear in this direction. This stuff is gonna be linear in this direction. And this other guy here is also going to be linear, which is the thing that doesn't cost me computational modeling power. Okay?
now can we put 150?
Yes, we can do 150.
Why do we need that for an exercise for the?
All right.
We'll just check and then we can go. Really?
Yes.
150.
Not good.
There you go.
Yes. Up to 5.
Yeah, but
Pardon.
Voila. And now you can see much of a smoother curve. Other questions? I think if we have 2 minutes, yes.
The way we chose y was like 1001, and then correspondingly we chose our cost function to be y hat times c minus log of y hat times c. So this can only do classifications, right? So if I want to do something that's like a prediction problem.
Yes, if you are going to be doing a prediction, you're going to be basically using an MSE, mean square error, where you're trying to see what is the quadratic distance between your target and your own prediction. Okay,
So that's a different cost
and
function.
this is going to be a different cost function. That's correct. The other question?
Could you add a fourth classification that just says it doesn't belong to either of them? Would that improve your accuracy but not add more computation or like a little bit of more computation?
But which kind of samples would I put there?
Just everything else. I mean, could you generate them? Or
But where would you put them? Right now we have 3 different classes. You can have, okay, but this applies for other, I understand your question. So maybe if you do like face recognition, maybe you have like 5 different identities, and then you would like to have an others identity. Is it something like that, right?
Yeah.
So what I've seen that usually having the other category is bad because it tries to get all together. So the network's gonna try to put together things that are different, rather than having more classes maybe. And that's actually easier because the network has to just group smaller regions. So these ones are just relatively small. If you have different things that are all around and you try to have them together, the network will try very hard to somehow push those things together. So the other category usually is not a very good idea in this case. One more question? No? If not, thank you so much for listening. And if you have any other question, I will be outside here. Thank you.